So, welcome student to the foundation of classical electrodynamics course. So, in under module 2 we today going to understand the few problems regarding the different kind of charge distribution, and then we will introduce the Gausss law. So, we have class number 24. Okay, so let us directly start, because last day we discussed about the charge distribution, how electric field can be calculated from different charge distribution. So, let us take an example 1, how to execute this in a problem. So, a very standard example. And the problem is, if I have a infinite wire, and then this is a infinite charged wire. So, this is so for infinite charge wire. So, suppose I put my origin here, and along this direction is my z direction, and it is suppose it is placed over x direction. So, this is my x coordinate, and this is the way it is distributed over x axis, and it is extended infinitely. The problem is, what should be at any point, say over here at any point d over z axis, what should be the electric field, because of the presence of this wire, which is infinitely extended and charged particles. I mean it is a charged wire. So, in order to execute this problem first, so let us, because this is infinite wire, so the contribution of each and every point should come here, all the points, and then there should be a vector summation, and we will see that due to the symmetry these components will cancel out, only along the z component will have the non-zero values. So, let us take a small segment here, we call it dx, and from here to here this is x distance, say. And now for dx segment, let us try to find out what should be the field for this dx segment at this point. So, suppose this distance is r. According to our notation, we always put this curly r when we want to find the value, or when we define the distance from the from this source point to this field point. And let us consider that this is making an angle, this is making an angle with this point, this is making an angle, say theta. So, the electric field of dx section will be along this direction. If you divide this electric field into two parts, along these and this, by symmetry you can see that, and this side also we have a dx here, and this portion will cancel out. So, whatever we have is only the z value, the z direction. So, this is roughly the geometry. If this is theta, then this has to be theta as well, and this length is d from here to here. This is O, origin to this field point is d. So, straightway we calculate the z component for this dx, z component, not x component. So, the z component, if I calculate, it should be 1 by 4 pi epsilon 0, and then the charge distribution over line is lambda, and for dx it is dx. So, lambda dx is the amount of charge we are having here, which is dq. Okay. Instead of writing dq, I straightway write lambda dx. Now, what is the distance? Distance is r. Directly I write r in terms of the given x plus say d square, that should be the value of r square, this r. So, this r is equivalent to x square plus d square whole to the power half. Okay. So, and then the cos component, no, not the cos component, because this angle is theta. So, then the sine component. Different way you can do this problem in different way. So, now this things is 1 by 4 pi epsilon 0 lambda dx. Let us put in terms of r, because it seems it should be easier if I execute in terms of theta by taking the range. Now, the cos theta. So, now the next thing is to find out theta in terms of r, that is all. So, cos theta, it is simply x divided by r according to this geometry, because this is theta. If I want to find out cos theta, it should be x divided by r, and sin theta is d by r. That makes tan theta is equal to d by x. These are the information we are having right now. Now, if I make a derivative of this quantity, so I know that sec hyperbolic sec square theta d theta is equal to minus of d x square, and then we have dx, which is minus of d divided by x, I know in terms of, so this is cos square theta by r square dx, right. So, dx in terms of theta, if I execute, it should be simply minus of r square, cos square, and this become 1 divided by d and d theta, which is in terms of sin theta. If I just eliminate this r, is minus of d divided by sin theta square, sin square theta, and d theta. Okay. So, I just write dx in terms of sin theta, and I am going to put it, and r square I can write in terms of sin theta as well. So, everything is now in place. So, I simply write d of E z is simply 1 by 4 pi epsilon 0 lambda divided by d square lambda divided by d square, yeah, because I am writing this r square in terms of sin and d. So, r square should be d square divided by sin square. So, I should have one sin theta here, sin theta, that is the component due to z, and let us put this sin square theta, and later I put sin theta, and dx is minus of d of sin square theta and then d theta, and the z component I will have a sin theta already. I am talking about this sin theta, which is already there. Okay. So, this sin theta and sin square theta will cancel out. So, that basically leads me to minus of lambda 4 pi epsilon 0. 1 d seems to be cancelling out here as well. So, we should have a d here sitting, and then simply have sin theta d theta. So, this is for the segment dx. Now, if I want to find out the entire field, then I need to integrate it, and this integration. So, for entire field E z should be integration of d of E z, and that value is simply the integration of that quantity lambda divided by 4 pi epsilon 0 d, and the integration of sin theta d theta. Now, you have to be careful enough to put the limit here, because now I am taking all the infinite length. So, there should be a limit of theta, and if I go from if I now move this dx from here to the infinite distance, here to some infinite distance, from this point to some infinite distance, then the theta will vary from pi by 2 to 0. So, I should pi by 2 to 0. This is the variation of the theta we should have when I extend all the length. Not only that, this is for one direction, this is for in this direction from here to here. If I go from this side also, then by symmetry I can just simply multiply a 2, that is for other side. By symmetry I can do that. So, now if I execute this stuff, I should simply have 2 lambda divided by 4 pi epsilon 0 d, and it should be the minus sign is there. So, I should have a cos theta with a negative sign after integration, and if I absorb this minus sign, by the way, I can go from 0 to pi by 2, and that eventually gives me, because cos pi by 2 is 0, then it should be like 2 lambda divided by 4 pi epsilon 0 d, and that is all multiplied by 1. So, this quantity is simply 1 by 4 pi epsilon 0 into 2 lambda. This is a constant value you are getting by d. So, you are getting a constant value when you are having a fixed d. Now, if we increase the value of the d, that is, if you go more and more over z axis, there should be a decay, and it only depends on the charge density lambda. So, this is the value of the electric field for infinite distribution of the charge over line. Now, with the same note, I can go forward. For another problem, or say example. So, in this example, what we take is the surface charge for infinite surface. So, surface infinite, we should have an infinite surface with surface charge density sigma. So, what is the problem? So, I am having, so let us first draw my coordinate system here. And okay, I need to draw in a different way because this is surface. So, maybe it will be easier to, this is x, say, this is y, and this is z. Suppose the surface is in this plane. So, the surface in xy plane and it is charged, this surface is charged with a surface charge density sigma. The question is, over a height h, from here to here over a height h, if I want to find out the electric field, what should be the value of that electric field? Very standard problem. Later we will going to solve this with much ease using exploiting the Gauss's law, that maybe today I am going to introduce. But let us first do that in a standard way. Standard way means in just doing everything rigorously, exploiting the Coulomb's law. So, let us have a point here, small section like this, small surface like this, and from here to the surface, this point say r vector, and from here to here, from this coordinate, this length is say rho. So, this is a rho vector and this say phi. So, I am using a cylindrical kind of system, because I can I can change my phi and rho together to find out the value here, because this is a surface. So, the surface element, now we know the surface element ds, the surface element which is rho d rho and then d phi. This is the surface element I can have. What is r here, by the way? Vector r. Vector r is h, because this is h. So, h with the unit vector z minus rho with unit vector rho, because this is rho, this is from here, this is h, the length. So, I can find out r in this way. Okay. So, what is r squared then? R square is simply h square plus rho square. Just make a dot product and you will going to get the result. Now, what is dE here? dE vector, that is sigma ds, due to ds if I want to find, divided by usual 4 pi epsilon 0, that is there, this is dq, sigma ds is my dq, and for dq I am getting this, and then r vector divided by r cube, okay, that is my dE. Now, if I put everything, so it is sigma divided by 4 pi epsilon 0, and then rho surface element, if I write rho d rho d phi, rho d rho d phi looks good, bad, dou d phi divided by r cube, in terms of h and rho it is h square plus rho square whole to the power 3 by 2 that I have, and r unit vector is h z unit vector minus rho unit vector, right. Okay. So, now if I try to find out the total electric field E, it should be integration of dE, again it should be the z component, because by symmetry you can see that all the components that we have should vanish, all the component that is parallel to this xy plane should vanish, and only we have this z component that sustain. So, it is z unit vector along this direction I want to find out. Then let us write this value. So, this rho component I can eliminate, only thing that I have in my hand is h and then sigma, then it should be in z unit vector direction, and then I have 4 pi epsilon 0, 4 pi epsilon 0. Then I integrate it over rho, because now rho and phi will going to change. So, by integration rho goes to 0 to infinity and phi goes to 0 to 2 pi, and I am having this problem, 0 to 2 pi. Okay. So, then I have rho, then d rho, then d phi whole divided by this quantity, say rho square plus h square whole to the power 3 by 2. Okay. Fine. Now, I have h sigma divided by 4 pi epsilon 0 and then z unit vector, and then phi integration I can do because this is not a function of phi. So, I have 2 pi outside and the rest of the integration is only over rho. Rho should be 0 to infinity with this value. So, here we are having rho d rho. So, I can have 1/2 here to write it is as d rho square divided by rho square plus h square whole to the power 3 by 2. Just manipulate here by just writing d rho square. So, now my integration is easier. I can simply have h sigma divided by 4 pi epsilon 0, and then this half I should have pi by 2. The unit direction should be z, I should keep it, and then I should simply integrate 3 by 2. If I now d rho, so this is I can just write this as x d rho square plus h square is equal to x. Then I simply have the integration like minus of this is 3 by 2. So, I can have like 1 divided by half rho square plus square whole to the power half, right. It is 3 by 2. So, 3 minus 3 by 2 plus 1 divided by minus 3 by 2 plus 1. So, that is why minus half here and this quantity, and now the limit is 0 to infinity, and with this limit we simply have h sigma divided by 4 pi epsilon 0, pi by 2 is here, z unit vector is here. When I put infinity, so this quantity will not no longer be there, and when we put 0, then plus minus sign will go to absorb, and we simply have 2 here and then divided by h. So, this 2 will cancel out, this pi will cancel out, h seems to be cancel out, which is interesting because it does not depend on h anymore. So, that is a very significant. So, simply we have sigma. So, so this 2 is okay, pi by 2 is here. So, I am having a 2 here. So, 2 and so this 2 will cancel out. So, sigma okay. So, I should have 2 pi. Okay. So, previously I should have 2 pi here and then I have a half outside. So, this half I take, but this 2 I forget to cancel. Okay. So, yeah, so there is another 2 sitting here, so that I forget to cancel. So, please note it was 2 pi h sigma 4 pi epsilon 0 z unit vector 2 pi, and this half is coming out, and rest of the thing I invent a half. So, this half is coming out. Yeah, then I should have another 2 sitting here, 2 sitting here. So, we should have simply sigma divided by this 2 and 4 should be 2, and we should have epsilon, and that is all, z unit vector. This is a very important result, the electric field, that for infinitely extended surface, the interesting thing is that it is not depends on h. So, I started the calculation that what should be the field at h point, and finally I find that for infinitely extended sheet of charge, a charged sheet, the electric field is a constant. It is sigma divided by 2 epsilon 0 with z unit vector. Okay, so after that maybe we can naturally, it is natural that we can extend the problem for, so example 3. It is natural that we extend the problem for a spherical surface, not spherical surface, a sphere, charged sphere, and try to find out over say some z point. So, this is my z, at some point what should be the electric field due to a volume charge element sitting inside this sphere. So, this is a natural extension of all this problem. I started with line charge density, then I have the volume charge density, and now I can have an extension of this. But if you want to do this problem in a rigorous way by using whatever the rule we are having, whatever the law we are having, which is Coulomb's law, it will be a very extensive problem, very extensive problem. You can do that, I mean in principle you can do that by taking the proper integration, and you will get the result, but you can do this problem with much easier way if you know the Gauss's law. So, that is the thing today I like to introduce. I am not going to do this problem because it will be a very lengthy problem if I want to calculate in a standard way, the way we did for other 2 problems. On the other hand, if I use the Gauss's law for this problem, it will be very simple. So, let us now introduce the Gauss's law today. So, the next thing, the problem I am not going to do here as I mentioned, because this is a very lengthy problem, and more sophisticated way and more simple way to do this problem by using this Gauss's law. So, I will just start Gauss's law, maybe we will continue this in the next class as well. So, the Gauss's law is saying, before Gauss's law, let us try to understand what is flux. Already we exposed with this term flux. So, the flux is d phi E, and that is E dot ds. Okay. So, that is flux. So, for a single charge E electric field, we know this electric field for a single charge is simply say sitting in the origin, it is q divided by 4 pi epsilon 0 and then r unit vector divided by r square, right. This is r divided by r square. Now, if I want to find out the flux here for this, so I should have a surface like this. So, this is the surface and I am having a point here sitting q. So, the electric field is going here and should cut the surface like this, and this is my electric direction of the electric field. But also the surface should have a direction here, and the direction is say n unit vector, and ds surface, whatever the surface we are taking here, the surface element is simply ds with n unit vector. So, for a spherical surface, if I have a spherical surface, my ds should be r square, then sin theta, then d theta d phi with n unit vector. This is the surface element for sphere. Now, n unit vector should be equivalent to r unit vector, since I am taking a sphere. I am taking a sphere where the charge is sitting at the center point here. So, whatever the r unit vector we have, that should be equivalent to the direction of the surface. Okay, so the total flux, if I want to calculate for the single charge sitting inside this sphere, it should be integration of d phi e, and that quantity is nothing but the closed surface integral of E dot ds. Now, E dot ds I can calculate, and by putting the value, because for a single charge I know all the values. So, this is q divided by 4 pi epsilon 0. I just write my value of E divided by r square, and then the surface element is r square sin theta d theta d phi d theta d phi, that is all, and r unit vector. This is a dot product here. So, this quantity simply q divided by 4 pi epsilon 0, I can take it outside the integral, and then d phi will be integrated from 0 to 2 pi, and r square, here you can see this r square will going to cancel out, there will be no function of r, and I should have sin theta whose limit for closed circle is 0 to pi, and then d theta. So, this quantity gives us 2 pi, and this quantity gives us pi. So, if I put this, you should have q divided by 4 pi epsilon 0 into 4 pi, which is q divided by epsilon 0. So, that means, if I want to find out this closed integral E dot ds, then that value is q divided by epsilon 0, but this q, mind it, is inside this in this volume element, the surface is enclosing. So, inside this surface you are having q. So, I should write here something called key enclose, the surface is enclosing the charge q. So, that is one of the statement of Gauss's law, and we will discuss more about, today I do not have that much of time. So, next class we will discuss more about the Gauss's law and try to find out the more interesting result. With that note, I would like to conclude here. Thank you for your attention and see you in the next class.